started. It's 8-6 already. How and Alex were good after winning a coding competition together. After winning a coding competition together, what have they done? How to read the problem? Yeah. They received a huge pizza as their prize. Initially, they're given n slices of pizza each day. The following process takes place. If there are at most 2 slices of pizza, Alex eats all of them. If there are greater than or equal to 3, his hover splits them into 3 groups such that Howe eats 7 slices, Alex eats 2 slices, the middle group, and the remaining empty slices are carried over to the next day. When the maximum number of slices Howe can eat if he chooses the partition optimally. There are greater than or equal to 3 has to divide into 3. Maximum. Can he choose almost everything? We have to think of that. Just do this thing. 1 1 everything. 1 1 everything. Then he get almost everything. The other guy gets 1. So n minus 1 is the answer. No. 1 1. Okay. Okay. Each day this guy gets more, right? And then again 1 1. So every day this guy gets more. So if it is every day this guy gets more, and when it becomes less than or equals to 2 for the first time, that guy gets even more. So it is the best is this process is the best, let's say. 1 1 1 1 1 1 is the best, let's say. If that is the best, if that is the best, if it is odd, it is floor. If it is even, if it's even less, it's minus 2. It's if it is even at the last, you will be left with 2, and those 2 will be gone. N minus 2 by 2. Okay. If it is odd, this will work still. I'll just write it as 2 things. Okay. I have to be quicker. Be quicker. If it is odd, I think it's just n by 2. If it is even, it's just n minus 2 by 2, let's say. Okay. Last 2 things will be left out, and this one passed. If it is odd, I think it's correct. Whatever I have written is correct. Okay. Screen's visible, right? You're given n, I'll read C2. You're given an integer k and n positive integers written on whiteboard. You may perform the following operation. Choose an integer from the whiteboard and erase it. This operation can cost at most k times. Choose an integer x greater than or equals to 3 from the whiteboard. We can do erasers. Split it into 3 positive integers such that then erase x from the whiteboard and write 2 new integers x1 and x3 on the whiteboard. Note that x2 is discarded and not written on the whiteboard. This operation may be performed any number of times. Okay, we make them into 3 increasing things similar to the other one. The beauty of the collection of B is defined as the greatest common divisor of all. Formally, if it is, we can do arrays that many times. We can do split, and once we split, we discard one thing. So you can remove something such a way that x1 less than or equals to x2 less than or equals to x3. What does this say? X1 is less than or equals to It doesn't say much. Doesn't say much. You can remove some. You can split that into two parts such a way that one is greater than other, but the remaining should be in between. It says something. Yeah, we have to be a bit careful here. Formally, it is the largest integer d that divides that. You are asking to determine the maximum possibility of integers on the whiteboard after performing at most k arrays operations and any split. So n less than or equals to that, a values are also less than or equals to n. So we can do of n probably, and we have how many arrays we are allowed. Okay, split. What does split is? It seems very difficult. The problem seems very difficult, but we have to hope, we have to solve the problem. For given that we can do k erasers, we can do k erasers. Okay, g less than or equals to, and maybe we brute force because it seems difficult, right? It seems difficult. Maybe we brute force g, maybe brute force g. For g to be possible, this thing can always be thought about, right? For g to be possible, what should we be doing? Split things into g multiples, right? For x, each x is either splitted into g multiples, or finally it has been split into g multiples, or has been discarded, or some portion of it has been discarded after splitting into g multiples. Okay, either that or this. So if x1 is not g multiple, then you must split it again. Okay, as long as x1 is not a g multiple, you have to split it or erase it. Erasing before splitting is better. Okay, now splitting can be done any number of times, right? Okay, what I mean, if you are going to split, if this is not a g multiple, you have to you have to erase again in that. So erasing directly would have been better, right? So x1 must be a g multiple. If x1 is not a g multiple, what happens? If x1 is not a g multiple, what happens? Then after you discard x2, again you have to do one more operation on x2. You have to get rid of x2. You have to split it. You won't lose. Even if you split it, there will be one of them will be. Or if it can be made g x2 again g multiples, 2g or greater than or equals to 2g, something. If this is possible, then it's fine. Sorry for this. This can be non 2 multiple, and that can be removed, right? Getting a call. This doesn't seem that easy. I'll read B2. You're given n machines arranged in a circle, and where n is at most 20. Hello? Yeah, I think it's audible. Uh, where n is at most 20, each machine. Uh, the machines numbered clockwise from 1 to n, and the type of the ith machine is denoted by SI. Each machine takes an integer x and updates it according to its type. decrease x by 1, formally x equals to x minus 1, type b replace x with the floor of its value. So x minus 1 or floor, which is greatest integer less than or equals to y. You're given q queries, each of consisting of a single integer a. In each query, you start at machine 1 holding an integer a. For each second, the following two actions occur in order. The current machine updates a according to its type, then move one step clockwise to the next machine. Formally, if your machine at I, you will go to I plus 1. If you're at n, you will come here. This process continues until a becomes 0. For each query, determine the number of seconds required for a to reach 0. So n is small. Okay, n is small. If there was a b, if there was a b, you can brute force. If there was a b, you can brute force. Why? Every time one bit will be lost, right? Uh, in 20 operations, one bit will be lost. So it's a simple problem. It's just testing your brute forcing or proving or brute forcing things. If there is a b, that's it. If there is no b, answer is like answer is like if there is no b at all, the answer is different. Int nq sin nq b equals to 0, string as seen as for char c as if c equals to b equals to 1. Okay, for int I equals to 0, I less than q, I plus plus, int x seen x, see out. If there is a b, what should we do? If b equals to 0, see out x. Okay, that many number of seconds, right? Each second. Else you can brute force. You start at 0, let's say, while b, okay, answer equals to 0, while b, if s of I equals to a, mm, x minus minus, else x by equals to 2, I equals I plus plus, I remainder equals to n. Okay, see out answer. So there is b here, right? There is b here. So what's happening? Why is it being 0? I have to do answer plus plus. I have to be here. I have to be here. I have to be careful. Okay, B is done. C seems difficult. Let me read D2. Okay, maybe C is easy. Let me read D. Or else let me try to make some other observations. Okay, on C, can I make any other observations? Uh, if you can do this, then you need not do anything, right? If you can make it some G multiple, you need not do anything. Maybe this is like G plus R. Okay, and the remaining is very big somehow. If everything is in, the answer is in. We can write those things also. Okay, if all are divisible by something, the answer is that. You need not do anything. You can do some erasers at most k times. This is definitely brute force, probably brute force. If something, okay, if something is not divisible by g, okay, you can save it with zero operations. If you do g plus r remaining, or or you cannot save it, you will have g plus r or you'll have something smaller, then you cannot save it at all. So you can save it when this is greater than or equals to 2g. So the whole is greater than or equals to 3g plus r. Then you can save it. Else you can't save it. Okay. If it is greater than or equals to 3g plus r, you can save it, which is nothing but greater than or equals to 3g. Be careful here, like 2g, 3g, 4g. You can see it very clearly. Okay. If that is going to remain, erasing it would be better. It should have gone here. Whatever is not divisible, it should have gone here. Otherwise, you will do one more operation. Instead of that, you doing one more operation, you should have removed it directly. You could have removed it, right? So this should have been the taking all the remainder. And now you have greater than or equals to 4g. You need not save them. All of them are saved. And now if you look at the remaining things, so for each g, when you are brute forcing, you have to see, is there something less than or equals to 4g? Okay. So you want number of non-divisors less than or equal to 4g, less than or equals to k, so you can throw them all away. Okay. Less than 4g cannot be saved. Less than 4g cannot be saved. Okay, number of things less than 4g, they cannot be saved for sure. You cannot save them. We have proved it very clearly. And if they are less than 4g, if they cannot be saved, you want that count. Okay, you want that count. If you have frequencies of everything, you can take prefix array to get the count of less than 4g. Okay, you can take prefix array to get the count of less than 4g. And then what do? You remove count of g multiples, 2g multiples, 3g multiples. Okay, then you have less than 4g which are not divisible by that, and then you're done. The problem is done. I guessed it, it's brute force, because the structure of the problem, if there is a simple proof, it demands it to be brute force. See? Does this run? I only need frequencies. I don't need anything else. G can be 1 in the worst case, right? Everything is G multiple, right? Int pos equals to frequency of min of n comma 3 times of g, 4 times of g minus 1, let's say. Okay, less than 4g. I want less than 4g. The number of values that are less than 4g minus frequency of, I'll just write this one. Fuck it. If g is less than or equals to n, right? Pos minus equals to frequency of g. If 2 times g less than or equals to n, pos minus equals to frequency of 2g. If 3 times n, g less than or equals to n, pos minus equals to frequency of, it's just some observation, easy observation. Okay, If pos less than or equals to k, this definitely happens for g equals to 1. Okay, why you are adding that? Pos will become 0, c of g return. This will definitely happen for g equals to 1. Okay, how is this happening for 9? How to make it prefix array, right? So it's pausing. Simple small observation. Okay, simple amount of logic. If there is a reminder, the goal is to make them all multiples. Okay, this is an interactive problem. You're given a hidden permutation p of length and you're allowed to interact with it by asking the query at most 2n times. We have 2n queries. Select two integers I comma less than I less than or equals to. It's not the last element on x. The graded will respond with 0 if pi and x is equals to 0 and 1 otherwise. The fuck? And equals to 0 and equals to 0, it's not all, it's and equals to 0 means all the bits active here, if they are all 0, sorry, all the places where there is 1, if all of them are 0 only, then you get 0. Okay, so you choose a subset. Why the fuck it is not pausing yet? The goal should determine the value of the last element of the permutation Pn using at max 2n queries. You don't determine everything, but you determine the last element Pn. Okay? You determine the last element Pn. You determine something that doesn't occur here at all. You determine something that doesn't occur here at all. Seems a bit tricky. We have to think for a while and then we have to answer that. Okay, the operation, we have to give importance to the operation. Okay, you give some bits. X is just some bits, right? You give some bits. What does it give you back? You give some bits, and what do you get back? Only if all of them are 0, it gives 0. So if any of them is 1, is active, it gives 1. So it's very specific to these are having good information, right? This says that zeros are nice. It says that all of those bits are 0. Okay. Okay. X is greater than or equals to 1 and less than or equals to 10 in n, but n is small, permutation would be small. Maybe some, are there any, see, in interactive problems, always look for valuable information queries. Okay, look for valuable information queries. I don't know what's valuable information. Okay, what's valuable information? There is some element will have all ones. See, finding lost element seems difficult. Maybe we'll find everything. Okay, how do you find something very quick? What is the query? How do you find something very quick? You give an X, what do you get? You cannot query last element. Can you determine some bit of? I'm thinking unnecessarily difficult. Now I need not think of like binary. I need not think of like divide and conquer. Let me not think first divide and conquer. Let me think something. Do you find all less than n? Maybe, right? Otherwise, how is it possible that you can determine this is that? You have to prove that. You must prove that everything else is before that. Otherwise, if you cannot prove that this value is not here, then that value could have been here, right? You have to find all of them. That is for sure. How do you find all of them? How do you find all of them? Just look at last bit. You know number of zeros, you know number of ones, right? You know number of zeros, you know number of ones. If you look at last bit, all of them will be almost half half zeros, half ones. And then with respect to last bit, you can identify what is the last bit of this shit, because you know what is missing, right? And then now you remove these things. Now you go over them. It's divide and conquer. 2n sounds divide. 2n says it's divide and conquer. It's divide and conquer. I can do it in a minute. O of n, discard other half. You can do this. Okay. It is divide and conquer. I will literally throw off elements. Okay. I will literally throw off elements. I will literally throw them off. And then I will calculate number of bits here, number of bits here, number of 0 bits, number of 1 bits. Based on that, I'll decide to keep one of them. Okay. We have a set of possible indices. Okay. We have a set of possible indices. We have a set of possible values. Okay. We have a set of possible indices. We have a set of possible values. I'll check the last bit of everything. But will they be equal? 0 1 0 1 0 1 0 1. Once you chop these zeros off, they will be equal. They will be equal. Okay, they will be equal. So J will be current bit. Okay, J will be current bit. So I will split them into half half. Okay. I'll split them into half half IL IR. based on the last bit. Okay, I'll split them into I0, I1. Okay, this bit was active. V0, V1. Maybe there is a simpler solution, but I always get somehow divide and conquer idea in my mind, so I'll go further with it. Now I have to see. Okay, if this bit is active or not. If that bit is active, so now I am splitting them. Okay, so what does this mean? Based on that bit, you have split them. Okay, based on that bit, you have split them. So so whichever is not equal, in you have to go and find among them further. Okay, you get it? If v0 dot size of not equals to v I0 dot size of, else, okay, so if v0 dot size not equals, means that 0 was here. Now you have this v0 is the possible values. Okay, so you don't do anything because that means that bit was 0. Okay, fun of I0 v0 j plus 1, and you not even do that. Okay, fun of I1 comma v1 comma j plus 1. I'll just submit this and see. I'll once see if there can be any error. No, size will become half. whichever size is not equal, that means some value is not here, that value might be here. Okay, so now these are the possible values again. So because now these are the possible values, among them we have to try to find further what can be our thing. So for that, what do? We again check the last j plus 1 bit. Based on that, we split them again. We proceed further. Seems fine for me. I should have submitted and thought whatever I was thinking. Did I do Endel? I hope it goes idleness. I hope it goes idleness limit on test 1 and not on test 2. This is an easy problem. I don't think so. Divide and conquer. It's not that easy. What is happening? I don't think divide and conquer is that easy for people. Maybe there is an easy problem, but I don't think there is an easy problem that easily. Fuck, fuck, fuck. I should not hurry like this. I know I can solve quick, but I should not be hurrying, right? I should be calm. I should be careful. Just because I can solve quick. Fuck it. Mm. This is correct. This is correct. Why should this happen to me all the time? Okay, am I doing entirely reverse? Now, if that beta is active, okay, I won't waste my contest here. See, I was doing good. Okay. I am assuming it is 010101, but it is not. My assumption was my assumption was elements start from 0. Okay, this was my assumption. Okay, so I thought if we chop off the last one, again we'll have 010101, but then 0 is missing. What I have done would have worked if V is slightly different. Okay, if it is starting from 1, then what? If it is starting from 1, how would it differ? Only 00 is missing, okay? If it is starting from 1, if the first value is 1, then we are good. Okay, then we start from 0. But that is not 1, but that was 0. Then we will start from here. Okay, then we will start from here. And then again, if again it was 1, then we will again start from here. Okay, but again, if here it was 0, the first time 0, we choose 0. Okay, the first time we choose 0, from there my solution is correct. But if we keep choosing 1, what happens if I keep choosing 1? 1 minute. If I choose 1, oh, if I keep choosing 0, then what happens is the question, right? So now you have 0 here, and then you will have those values starting from 1 again. So even this seems to be fine. Even for this, it again starts from 1. But for this, if you choose 0, it starts from 1 again. Okay. If you choose 1, it starts from 0. In both the cases, things will become half half. In both the cases, things will become half half. So we are good. Can size be 0? I don't think so. It's wasting my time. It's wasting my mood too. It doesn't give us value, it gives us what it is, right? Fuck. 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 I saw it at 37 minutes. See, I am good, but I don't know why I do this. I just don't know why I do this. All the time. That's why I'm streaming so that people can know that I'm good. This is the easy version of the problem. The difference between the versions is that the version in this version the constraint on n is smaller. Okay, we have smaller constraint. It seems you're given a permutation P. You may perform the following operation any number of times. Select three distinct indices I, J, K such that both of the following conditions hold true. Pi equals to max of Pi, Pj, comma Pi, K plus 1. So Pi is here. One of them is slightly smaller. The other thing can be any small one, smallest, and Pi equals to minimum of Pi, comma. So it is Pi minus 1, Pi minus 2. Okay. So minimum is maximum is pi minus 1, minimum is pi minus 2. Then decrease pi by 2, increase both pj, pk by 1. Seems a nice problem it is, right? I mean, we have some operation, it seems to be a nice problem. It can be proven that p remains a permutation, that we can see, obviously. Your task is to determine the lexicographically smallest permutation that can be obtained after performing the operation any number of times. So it's a good problem. It's about seeing the operation for what it is, seeing the operation well. Okay, I'll come in a minute. I think I have solved this one, two, somehow. At least I have seen something nice in this one. At least I have seen something nice. What have I seen? What have I seen? If you look at the operation, it's just choose three adjacent values. Okay. And then swap x minus 1 comma x plus 1. Okay, so if you look at p inverse, okay, what does it say? If you look at p inverse, it's just swapping to adjacent, swapping I comma I plus 2. Okay, you can just swap these two things. That's what it is. Means you can order them as you like. Wait, why is it this easy? So now you want lexicographically minimum. For this one's inverse, if it was lexicographically minimum, P inverse, it's just sorting. But it's not. It's lexicographically minimum. We have two sets. Okay, these sets can take these values, these sets can take these values. You want one to be occurring, one to be taking the minimum possible value. Okay, you want one to be taking the minimum possible value. That's your first goal. So one goes to the minimum possible value. Then two. Wait. Am I wrong? It can't be this easy, right? Let me try to test it on this test case. Okay. 1, 3, 2, 1, 4, right? Means what is P inverse? 1 is 3, 2 is 4, P inverse of 1 is 3, 4, 1, 2. Okay. And what is happening here? This becomes minus 2. Oh, okay. It's a cyclic shift. I plus 1, I plus 2 will become I plus 2, I, I plus 1. That's what you can do. You can move something. You can move something two times before. You can move something twice before. Okay, that's what the operation is. An operation is you can move something twice before. That's the operation. You can take anything, you can move that twice before. This is the operation. Sorry. If this is the operation, what is the minimum value that one can take? Where is 1? You cannot change P inverse of 1, P inverse of 2. Okay? You cannot change these two things. You can change them. You cannot apply the operation on them. Okay? There is something you cannot change. There is something here that you cannot change. What you cannot change? Okay, let's think about the problem. What's the minimum value one can take? See, I think it's always starts with 1, I thought. But then here you cannot take 1, it seems. 1 cannot be minimum. So there is a case. Why cannot 1 take minimum? You have 1. There is some index that cannot come here. There is some index that cannot. 1 cannot come here. Means whatever 1 do, 1 cannot come here. 1 can only come to 2. What does that mean? 1 cannot come first. You can move twice, but 1 cannot come first. If it is in the odd index, let's say, if 1 is in the odd index, in the even index, in the even position, it always remains in the even position. Okay, see, what this means is, let's say this was that 1 is in the even position, right? So whatever you do, one can come to only whatever you do, one can only come to even positions. Okay, if one is in even position, it can only come to even positions. So that's what it is. So one can either come to now one can either come to 1 or 2. Okay, now if that is fixed, if one can come to 1, is the problem solved? Is my question. Why? Is there any benefit that this is coming here and then again this should come here, right? I don't think there is any benefit of doing that. In this case, 1 cannot come to first position, 2 cannot come to first position, 3 cannot come to first position, it seems. If all of 1, I'll just write it. What is it? 4 P inverse. 4, 1, 2, 3, 5. 7 is in 6th position, 6 is in 7th position, 8 is in 8th position, 9 is in 9th position, 10 is in 10th position. So what does this mean? 1 cannot come here. Yeah, whatever you do, even if 1 minute, if this comes here and then 1 can go there, right? Am I again wrong with my operation? I less than j less than k. Okay, 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 okay. I'm again wrong with my operations. So what does I less than j less than k means? It's fine. I have worked on the problem at least, right? So you want to have I less than j less than k means what? So I plus 2 should have smaller value. Okay, means a smaller value can move 2 steps before bigger values. This is the operation. That's all it means. If I plus 2 is smaller, I less than j less than k is always true. You swap them accordingly, right? Because max and min doesn't restrict any directions. Okay, you can swap them accordingly because it's symmetric, right? All these things are symmetric, so you can swap j comma k. Smaller value can move twice before. That's the operation. Smaller value can move twice before means 2 can move twice before, but then 1 can never move before. Okay, so 1 being here is the minimum. Sorry, what is the smallest value that can come here? 2 can come here. Nope. Nope. For 2 to come here, what should happen? Okay, for 2 to come there, what should happen? That is why. Okay, smallest. Okay, it is correct. 2 can never come there. 2 can never come there. So, smallest place 1 can take is 1. Smallest place 2 can take is 2. Smallest place 3 can take is 4. Smallest place 4 can take is 1. Okay, that's the answer. This is the answer. What have I done? I should have written this one. 4, 1, 5. Okay, this also gives off something. 1, 2, 3, 4, 5, 6, 7, 8, 9. Is it like that? Is it always like that? Is it like 1, 2, 3, cycle remaining things? Is it like that? Because if you generalize these things, guessing from the test cases, 4 comma 5 has been cycled, right? See here. Nah, guessing is bad. What can I do? I think there is some fact which can be used to solve the problem. So let's solve the problem. Only smaller value can cross two bigger values, right? Now we want minimum place one can take, minimum place two can take. First goal is minimum place one can take. Okay. Can anything bigger cross one? Now, nothing can cross one. So one can only go forward. So one can always go forward and nothing can cross one. So move one, surely. Now you are at two. Now you have moved one. Now how far can two go? Two can never cross one. Okay. But two can try to go forward. Okay. Now three, as much as as forward as it can try to go. Okay. Now three's turn. Is it just brute force? Three can never cross these two things. But three can try as much as it can. Okay. And once you know all those things, the next thing, it can try as much as it can. It has some smaller things before that. Can it go first? Can it go first? If you remove 1, 2, and 3, for 4, the earliest it can go is, think of it very carefully, earliest it can go is among the remaining things trying to go forward, right? So before anything crosses that, I will try to move this forward without. Is it moving bigger things first better without crossing any smaller things? 10 will be right here. 9 will be right here. 8 will be right here. No, 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 no. That's also not being right. First, we know one's position is this better. Is that position possible or not is what we have to determine, right? Let's say we are solving it in of n square. All of these are taken. Okay. These things are coming here. This is the case here. Okay. One can be go till here, two can come till here. Things can only move forward. If you look at greater than or equals to I things. Okay. Here one can move here, and then two can move here, and then three can move here. Things can only move forward given that these things are going to come here. Okay, how forward can this one move is our question, right? These things are coming here. So 1 to I are coming to these places. Given this, how forward can I plus 1 move? So move I plus 1 first, as much as you can. Now move all the remaining things to their places. You have few green things less than or equals to I ones, okay? You have red things greater than I plus 1. You have I plus 1 playing the game. So green things are coming to their position. You have red things. I plus 1 can never cross a green. It can only cross even number of red things, okay? It can only cross even number of red things and then they are coming forward. So what will I plus 1 do? It will try to cross even number of red things, okay? It will try to cross even number of red things as long as it can. If this was that, it will try to cross even number of red things. Let's say, let's say initially it's between two of these greens. It can never cross greens, right? And it will try to go as early as possible among these reds. Now, again, this keeps going, let's say, forward. So, all of those things try to go as forward as possible, okay? Before this moves, this will move. And then you have these things. Now I plus 1 will go as forward as possible among them. So for I plus 1, the best is move everything here and then try to move this. Now it crosses as many red things as possible. And now the problem is done. Okay. Among red, how many red will be before that? 0 or 1 is the question. Okay. 0 or 1. How many red will be how many red will be before I plus 1 is the question. Okay. How many red will be before I plus 1 is the question. To answer that, how many red that will cross these things finally? So green's final position will never have will never have two reds in between. Okay. So you know what are number of reds. Okay. You want number of reds before I plus 1 finally. You know it cannot be 2. So as I moves forward, as the previous green, as the before green moves forward, okay, as the before green moves forward, you will keep getting reds here. So you have these many number of reds before that now. Before I plus 1, you have these many number of reds. Okay. And you know finally number of reds that are going to be here. I think it will take the first red position over here. Hmm, among reds, it will try to be as early as possible. As many number of reds it will try to cross as possible. Okay. Now it is here. How many reds can it cross? Is the question, right? How many reds can it cross? Only these reds it can cross. And it will try to cross all of them, let's say. Some reds will come here, it will try to cross as much as it can. And that's it. Number of reds before here. So I think I am able to do this. I am able to get this, understand it a bit. Number of red before it. I think I have my algorithm. I will make it red green because n square, right? I'll just make it red and green. So what is it? Once you fix all red, among the previous things, it can either take this. I can do this. I'm overcomplicating it. It should be easy. It's just moving forward. Greens move forward. Number of reds before that. A number of reds before that. It's just parity of number of reds. Okay. These many reds it cannot cross. These many reds it cannot cross. These many reds are now before that. That's it. So how do I do this? These many reds it cannot cross. Okay. These many reds are before that. With this we can know what is its red's position, right? Okay. That's it. So I'll just move one. I'll just fix one's position as 2. Q inverse of 1 equals to 1. Sorry. P inverse of 1 remainder 2. If it is odd, it is 1, else it is 2. Okay. Q of Q. I think we are working on Q inverse first. Okay. So 1 has been, we know 1's final position. So now for I equals to 2, we need not do that because 2 itself could have been before, right? Okay. We want number of red before it. Okay. We want number of red before it, and then number of red will remain. We want parity of that. We want where one is. Where one is I want where one is in P inverse. Where one is in P inverse is what I want, which is nothing but P of 1. Right. So it is P inverse of J equals to 1. J equals to P of 1. So we are, this is J. As long as P inverse of J greater than I. I'll keep it V maybe. I. As long as the values are greater than I, I'll try to take this thing. Okay. Now, now, if j not equals to 0, if j not equals to 0 means there was a green before. So now what would I do? I will go and see. These are number of reds before that. Okay, that is done. If there was a green in gj equals to 0, else gj equals to, else if gj equals to, I'm writing complex code unnecessarily, gj equals to j. So this will have, if gj not equals to 0, so there was a green before. So where would this, this green might go because something else comes here, but mm, I'll make an assumption. Because there's no time number of greens before that. Number of reds before that. Okay. One minute. Isn't it the first green after this? Isn't it the first red after this? It's simple. Number of reds between that and this green doesn't change. So now we know number of P's in between. Okay, so now from j plus 1, it's cth 0. Okay, if c equals to 0, q inverse of k equals to, I'm fucking it up. I think the previous one was better. These many red things were before, now there are these many red things has been gone. So now among these many red things, now you do the problem. For int k equals to gj plus 1, k less than or equals to nk plus plus, if q inverse of k not equals to 0, continue. If c equals to 0, break q inverse of k equals to I, else c minus minus. For int I equals to 1, I less than or equals to n, I plus plus, q of q inverse of I equals to I. So we have one here, and then I'll also output P inverse. So one has moved forward, and then what happened to two? What happened to two? Why hasn't two moved forward? It's probably wrong answer on test too. Fuck it. It's a lot easier than what I was doing, I guess. 339 solves means, right? I thought more probably. It's probably much easier. It's probably much easier. It's just moving things forward. All of that I have thought, even if you move things forward, it would be the same thing. It would have been the same thing. Just moving things forward would have been the same thing. Just moving things forward would have been the same thing. I don't know why I thought a lot. Maybe can I do F2 with this work that I have put in? Maybe not, because it was complicating solution, right? Maybe this just works. Because that's what I was trying to do. I was trying to see the red things and move these things, see number of red things, but that's the same thing as doing it greedily. Ah, nah, nah, nah. My previous solution was correct, probably. Fuck. Mm-hmm. Krishna, come right here. I've been waiting for. Mm-hmm.